Hello, everyone. Welcome to the Brownbag today. I'm Sahil, Senior Data Scientist here at ELIZA. And today I'm going to talk about detecting driver distraction and drowsiness using machine learning. We'll start off by going through the project background and overview. Next, we will talk about the steps that are involved in implementing a machine learning solution. Then, we will go through the model and application evaluation. And lastly, we'll look at certain application results. So let's get started. The first question that arises is why care about distraction and drowsiness? Every 24 seconds, a human life is lost in traffic. It is 4 times more likely to crash when using a cell phone. Over 90% accidents occurred last year were caused due to distraction or drowsiness. And lastly, over 1.6 million crashes every year are due to distracted driving. This has led to a rise of driver monitoring systems, which has further accelerated due to the advancements in machine learning and computer vision tech. There is also an increasing number of regulations and compliance requirements, especially for the new built vehicles that require to have driver monitoring systems installed by default. Over 500 startups today are working in this industry, and the industry is projected to grow over $4.6 billion by 2031. We got the opportunity to work with Australia's leading provider of in-vehicle telematics to build a solution for detecting distraction and drowsiness using in-cab cameras. The key objectives of the project were to build a computer vision based proof of concept. The next thing was to make sure that this solution could be deployed on the NVIDIA Jetson device so that it can be run in real time inside the vehicle. And the most important one was to build a machine learning architecture and platform that enabled the team to iteratively improve and enhance this capability. So let's talk about the different steps involved in implementing a machine learning solution. Typically, a machine learning project is split into 4 stages: project discovery, data preparation, model fitting, inference, and deployment. The first phase, project discovery, is all about the why, what, and how. We try to define what the business problem is, acquire knowledge from subject matter experts, and conduct feasibility analysis to understand why we want to build a certain solution. The next is the what, where we try and define the project objectives and scope, identifies the risks and success criteria involved, and also identify any constraints that we need to keep in mind for designing the solution. And then we go to the how. We talk about the type of the solution, try and identify what the unit of analysis and prediction is. Do we really have the relevant data, or what are the steps that would be involved in capturing this data? And lastly, think about the different model selection criteria. We've already talked about the why, so now let's talk about the what. What is driver distraction? Driver distraction can be split into 3 categories: physical, visual, and cognitive. When talking about physical distractions, we can think of examples such as texting on the phone, eating, or drinking in the vehicle. Visual distractions is where the driver might have both of his hands on the steering wheel, but is distracted visually trying to read a text on the phone or looking at a billboard outside the window. And the last one is cognitive distractions, and some of the examples might include talking on a hands-free cell phone or listening to music on high volume. For the scope of the project, we decided to only focus on physical distractions, as these are the most common reasons for accidents. The next question is, what is drowsiness? Defining drowsiness is a bit more complicated than distractions, and one of the metrics that can be used to defining drowsiness is the KSS scale. 1 is when the subject is extremely alert, whereas 9 is when someone is extremely sleepy and is making a lot of effort to remain awake. For us, we tried to focus only on microsleep. where microsleep can be defined by very short periods of sleep that can be measured in seconds rather than minutes or hours. Next, let's talk about the solution constraints. The distraction and drowsiness detection needed to run in real time on a device deployed inside the vehicle at 30 frames per second. The models needed to be compatible with the NVIDIA DeepStream platform so that the solution can actually be deployed on an NVIDIA Jetson device. There was also a requirement to put in minimal effort upfront for manual data labeling. And lastly, we wanted to make sure that the system is able to cover a wide range of distraction and drowsiness scenarios. Let's now talk about the how. In order to detect physical distraction, we focused on implementing a solution which was based on certain machine learning models as well as application heuristics. The first step for detecting distraction was to identify the face in the image and then use a key point detection model to find key facial landmarks such as the eyes, nose, chin, and other key points. As you can see in this example below, the input video frame is fed into a face detection model. The cropped face image is actually used to detect the facial landmarks on the face. After calculating the facial landmarks, the next step was to focus on the nose center as the key facial landmark. The nose location was calculated across multiple frames, and what we then defined was this circle of uncertainty, which essentially is a mean of the nose position across a certain number of frames. And this helped to identify the common areas in which the nose is expected to be when the driver is not distracted. So initially, when the driver is moving around a lot, the circle of uncertainty will be huge because you will tend to move a lot when starting to drive. However, when you start driving in a focused manner and when you're driving without any distractions, you will realize that your nose position does not vary too much. And essentially, the circle of uncertainty, which is basically calculated as the mean and standard deviation of the nose position across a certain number of frames, will be much smaller. And once you have identified the circle of uncertainty, as part of the next step, you can detect distraction based on the nose position. If the nose location is outside this circle of uncertainty for more than certain seconds, in our case, we use 2 seconds as the threshold, the driver can be considered distracted. So that is how we detect physical distractions, by considering the nose position and any deviation from the standard nose position. The next question is, how do we detect drowsiness? This is built on top of the facial landmark model, where you essentially are then focusing on the eye points. We're trying to detect closure of eyes. The first step is to calculate eye aspect ratio, which essentially is calculating the width and the height and the ratio between the width and the height. When the eyes tend to be closed, the aspect ratio tends to be close to 0. So the first step is to detect the relevant eye points to calculate the aspect ratio. And the next step is to calculate drowsiness based on percentage closure of eyes over time. So that's the per clause method. And essentially what we're trying to do is, first we identify what the peak ratio is. For each individual, the eye aspect ratio will be different. And that is why we first need to identify what that peak ratio is for each individual driver. Next, we identify the max ratio, which is basically average of the last 10 peak ratios. And we consider the eyes being closed in a frame if the eye aspect ratio is less than 2/3 of that max ratio. If 80% of the frames in the last 1 second have closed eyes, we would raise a drowsiness alert event. So that was all about the project discovery phase, where we defined the why, what, and how. The next phase was the data preparation phase. And here we defined the different areas that we needed to be able to capture the relevant data. And for distraction, some of these included looking around, phone usage, eating, reversing the vehicle, and also driving not distracted. And with each of these scenarios, It was important to take into account different environmental considerations. For example, the lighting, whether we're capturing these videos with glare during the day or low light at night, along with variations in terms of occlusions, such as sunglasses, spectacles, or wearing face masks, or combination of the above. Similarly, for drowsiness, we defined base scenarios such as droopy eyes, closed eyes, yawning, or not sleepy, and similar variations in terms of environment and occlusion conditions. Once we had these definitions, we then went on capturing this data. And this was done by building a mobile app to capture the videos along with relevant metadata. Over 100 videos covering all these different scenarios were ingested, which was around 6,000 different image frames. And dashboard was also created to be able to capture the event data in terms of number of events per scenario and per category to get an idea of how much variation we have in our data set. The next step after data gathering was the data preparation. The first step was to convert the video frames into raw images. And as you can see, after the first step, the next one was the prepare model data set, which was essentially converting these raw images into pre-processed images, which involved resizing these images into a fixed dimension. The next was to generate a labeling job so that the images could be labeled for face detection boundary as well as the key points on the face. And this was implemented using SageMaker Ground Truth, which in the end outputs the labels along with the images. For the face detection model, we created a pipeline to label the face bounding box. And the pipeline allowed the users to input what scenarios to choose from, exclude certain scenarios, also had the ability to choose between the public and private workforce for labeling. So it could be either members of the team or a public workforce to scale up labeling to a large number of images in the future. We also had the capability to add images to an existing labeling job. For example, if we have already labeled 1,000 images, then we had the capability of adding additional images. We ended up labeling around 3,500 images, and this can essentially be extended to support future object detection models as well. The next labeling job was to label the facial landmarks, to be able to label face points as well as occluded points, the points that are not visible on the face, the key point detection model. And the landmarks was trickier to label because in an image you essentially are labeling pixels. And for our example, we start off with labeling 16 points on the face. We ended up labeling around 800 images, and this could then be extended to add additional face points needed in the future. The next phase after data preparation phase is the model fitting phase. We start off with NVIDIA's off-the-shelf pre-trained models, the face detect model, which is trained across a huge corpus of images and can handle images of various heights and angles or the different field of views and occlusions. The input for the face detect model is the pre-processed image, and the output is the facial bounding box along with the confidence score. For the face key points model, we started off with a pre-trained facial landmark model by NVIDIA called the FPE-net model. The output used was then used for the nose and head position estimation, as explained earlier. The output is the coordinates and the confidence score for the 80 facial landmarks that this model supported. So this is what the pipeline looked like, where you have the individual video frames. They then pass to the face detect model, and that model gives a bounding box. The bounding box image is then cropped and inputted into the facial landmark model. We then apply the application heuristic logic, as explained in the previous section, to detect distraction and drowsiness events. And you can see how in the first one, we are able to successfully detect a valid distraction. And in the second one, we are able to detect drowsiness. So the next step in implementing a machine learning solution is model evaluation, where we assess how well is the solution performing on the given task. One of the metric for face detection, which is an object detection task, is the intersection over union, where we're trying to understand how well does the predicted bounding box and the labeled bounding box overlap. And you can see in this image that if the IOU is higher, the intersection between the areas is much smaller. Once we've calculated the IOU metric, the next thing that we calculate is the confusion matrix. For the solution, there were two metrics that were important to measure. One was the precision, where we're trying to answer the question of how many detected faces are truly relevant. And this is affected by the false positives. And the next one is the recall, which is how many relevant faces were actually detected. And this is affected by the false negatives. For the pre-trained face detection model, we found that the precision was really high, around 99%. However, the recall for the model was 21%, which meant that over 700 images missed detecting faces out of the 890 images that were evaluated. Looking at the evaluation results, we then worked with NVIDIA to understand why the solution was performing so poorly, and this led to a change in the configuration, which resulted in improved performance. Precision went down slightly to 95%, whereas recall jumped from 21% to 91%. And the average model confidence was around 90%. Next step was evaluating the face key points model. So we built a pipeline based on the average Euclidean distance between key points. Recall was 76%, but the problem was the average model confidence. The average model confidence was 29%. This was particularly problematic in extreme head positions. As you can see in this image, when we have the head in the extreme right position, the key points are outside the eyes. However, the confidence score is quite similar to when the key points are accurately predicted. Improve these models and fine tune them on our custom data set. One of the common techniques for fine tuning models in computer vision is transfer learning. In traditional machine learning, when you implemented a model for a single data set, and if you had a new data set, you ended up retraining a model for the new data set. There was no way to share the knowledge from the first data set to the second data set. However, with advancements in transfer learning, it is now possible is to leverage the knowledge from the base model, which might be trained on a different set of images, and fine tune this model on a new data set. The advantage is that this will require fewer data points from your own custom data set and improve performance for your domain. These are some of the examples where the base face detection model failed, which included high contrast images, very low lighting, multiple occlusions, and incomplete faces. And the reason why the pre-trained model does not perform well is because the pre-trained model is trained on images captured indoor. So we fine-tuned the model and created a pipeline to run retraining, and this resulted in an increase in the recall for our face detection model and also increased the average model confidence from 90 to 95%. Similarly, for the facial landmarks model, we were able to increase both the recall and the average model confidence score across all the points to 40%. And you can see in the graph below how the average confidence score for the fine-tuned model shifted and was in a much broader range across all points. When you look at the average score for the left eye points, the confidence score then started to range from 0.2 to 0.9, whereas previously the maximum confidence score was up to just 0.6. And as you can see in these images, even in the extreme locations, the eye points are much more accurate than the base model. Now that we've got an understanding of how the models are fine-tuned, the next stage of the project was to evaluate the application as a whole. The goal of the application evaluation was to establish a performance baseline and evaluate the application improvements, which could either be the model or the heuristics over time. And to do this, we started off by collecting a benchmark data set of over 25 videos. These videos were manually labeled to identify the timestamps where there was a distraction or drowsiness event detected. We then defined the metrics that were used for evaluating the performance, and this process can be repeated for any change made to the model or the heuristics. So, in terms of the benchmark data set, we collected 25 videos. These videos had a wide variety of scenes capturing distraction and drowsiness across different times of the day, between color and infrared images, different camera positions. For labeling the benchmark data set, we used Label Studio that allowed easier labeling of frames, as we were now labeling videos rather than images. We calculated the precision, recall, and F1 score, which is basically a combination of precision and recall. We calculated the metrics for the baseline application, which was implemented using the pre-trained models. And then we calculated results for the improved application as a result of the model fine-tuning. The distraction application precision went up 2%, recall went up 6%, and overall the F1 score went up by 9%. Whereas for drowsiness, the precision went up 29%, recall went up 17%, and F1 score went up around 31%. And that was just based on the first iteration of model fine-tuning. And to summarize the project, apart from building a proof of concept for distraction and drowsiness detection, we enabled the team by developing pipelines for the different aspects of the machine learning project. With a single iteration, we were able to improve both the application and model performance. And these pipelines form a solid foundation for the team to quickly iterate over the solution and improve the system performance and scale the product after release. Let's now look at the results for the distraction and drowsiness detection application. And that's all for today. Thank you everyone for watching.